Now that we've talked about electron behavior, we're going to talk about that behavior and use it to explain chemical bonds. Recall that atoms are attempting to fulfill their valence shell because that is when they are in the most stable of states. Now, in order to fill the valence shell, atoms are going to have to interact with each other, and specifically, we're going to have interactions in the valence electrons between these atoms in some way. When those valence electrons interact, it's going to bind together the atoms in question, creating a chemical bond. And usually, once we have bound together two or more atoms, we call that a molecule. So if we have one atom of some type of element and its valence electrons interact in some way, we'll talk about what those ways are in a second, with another atom. So this line kind of represents a bond of some type for now. Then we create a larger entity known as a molecule. So the types of interactions that we can have between atoms to create molecules. We have covalent bonds, which are the result of valence electrons being shared between the atoms. And then we have ionic bonds, which are when electrons are exchanged between adjacent atoms. Okay, so what we're going to do is we're just going to talk about those specific types of bonds in a little bit more detail. Let's talk about what it might mean to share valence electrons first. So there's going to be cases where we have two atoms. Both atoms would like to have additional electrons in order to reach that full valence shell. But we kind of reach this issue where neither one of the atoms has a high enough electronegativity, aka neither one of them has a strong enough pull to take the electron away from the other atom. And so what ends up happening is that these atoms are going to share electrons to kind of satisfy both parties. And kind of what that sharing looks like is the valence electrons will bounce back and forth from one atom to the next. So let's look at two hydrogen atoms and maybe see how this might play out. We'll call this hydrogen atom A, and we'll call this hydrogen atom B for clarifying purposes. Each one of these hydrogen atoms has one valence electron and would need an additional valence electron in order to reach the full maximum capacity of the valence shell. So in this case, neither hydrogen atom is going to want to give up the one electron that they have, but they definitely would both like to have an additional one. So we definitely are going to reach this circumstance where sharing is kind of ideal. So kind of how that's going to look is that in this iteration here, we can see that hydrogen atom A has custody, at least for the moment, of both of these electrons. And so at this point, its valence shell is filled, and so it's kind of in that stable state. At some point, those electrons are going to drift closer or into the valence shell of hydrogen atom B, which we see over here. And now we have a circumstance where hydrogen B has a full valence shell, at least temporarily, and is in its stable state. And we just kind of ping pong back and forth between these two atoms. And again, each one of them, at least temporarily, has sort of that stable status. Now the question is, ultimately, how does this sharing look? Like, how much time are they really spending closer to one atom versus another? Is that relatively even? Is it kind of in the ballpark of one more so than the other? And the answer to that is it really depends on how evenly paired the electronegativity is between the two atoms. So there's actually two different types of covalent bonds, polar and nonpolar covalent bonds. Of these two, the difference is the difference in electronegativity. Nonpolar covalent bonds arise when you have two atoms that are sharing their electrons evenly or relatively evenly. Kind of the rule of thumb is if the difference in the electronegativity between the two is less than 0.5 or equal to it, then we would assume that they have relatively equal custody over the electrons in question. So in this example, we have a carbon atom and a hydrogen atom. The electronegativity, remember that's what this Greek symbol is right here. This indicates electronegativity. If we take the difference between these, so 2.55 minus 2.20 is going to equal 0.35. And that is less than 0.5. So we would say that a nonpolar covalent bond is going to be formed between these atoms, meaning the electron is going to be pretty evenly shared, the electron pair, between the two atoms. On the flip side, polar covalent bonds arise when the atoms are not evenly paired. One of them has a much stronger pole than the other one, okay? And typically we say that if the electronegativity difference is greater than 0.5 but less than 2, you're going to end up with a polar covalent bond. So in this case, we're looking at a pair of electrons being shared between oxygen and hydrogen. Oxygen has a much higher electronegativity at 3.44. Hydrogen is still at 2.20, and that difference is 1.24. And that's going to fall between 0.5 and 2. So this would be a polar covalent bond that is forming between the oxygen and the hydrogen atom. How evenly the electrons are shared is going to change whether or not the molecule, the resulting structure, is charged or not. When we have nonpolar covalent bonds, we end up with rarely neutral structures that have no charged regions to them whatsoever. And that's because your electron is negatively charged, but it's kind of spending equal amounts of time with each of the atoms. So overall, there isn't one portion that is charged. In polar covalent bonds, because the electrons are spending more time towards one atom and are closer to it, we're going to have some regions that are partially negative and some regions that are partially positive. And that's what this Greek symbol right here means, this delta. Actually, this Greek symbol right down here, actually I think it's called lambda. Doesn't matter what it's called. That symbol means partial charge. Okay, so if we see it, that's what that means, kind of if you were to say it out loud. And then as a superscript next to it, we put a plus or a minus sign. Okay, so the atom that has the higher electronegativity is going to always be the one with a partial negative charge in a polar covalent bond. So if we look at oxygen here, we can see it has the higher electronegativity, and so it's going to end up with the partial negative charge in the molecule. And the reason why is because, at least temporarily, that electron is spending more time towards the oxygen, and the electron is negative. So if you have all of these negative charges kind of lopsided over towards the oxygen is going to end up being partially negative as a result. Hydrogen is kind of getting the shaft here. It's got the lower electronegativity, so even though it hasn't given up its electron, it doesn't have, as much ownership over it as the oxygen. It's spending more time with oxygen. And because hydrogen's electron is spending more of its time near oxygen, it ends up with a partial positive charge as a result. This is really what it means to be polar, is to have charged regions. So polar covalent bonds will always lead to molecules that have partial charges, where the atom with the higher electronegativity having the partial negative because it's hogging the negatively charged electrons, and the atom with the lower electronegativity possessing the partial positive charge. Kind of the last thing that we need to consider about covalent bonds is how many electrons are ultimately being shared between said atoms. So if you have a single covalent bond, then kind of what you're referring to is a pair of electrons that are being shared, aka 2. You can kind of see this in the schematic drawn between carbon and hydrogen, What I've done is I've circled the pair of electrons that would be sort of ping-ponging back and forth between the hydrogen and the carbon atom. Now, while this picture here at the top is a completely valid way to show that connection or that bond, drawing structures like this, especially for larger molecules, would be really tedious. So a lot of times we use something called a structural formula, which is kind of here down below. And in these, one line basically equals a single bond or one pair of shared electrons. So the line represents a pair of shared electrons. You can also have double bonds where you're sharing two pairs of electrons or a total of 4. You can see that occurring right now between the carbon and the oxygen. And if you wanted to draw that with the structural formula, you would just draw 2 parallel lines between the elemental abbreviations. And then finally, you can have a triple bond where 3 pairs of electrons, or a total of 6, are shared between 2 atoms. And kind of what that looks like is just 3 lines drawn stacked on top of each other, parallel to one another. The way we determine whether a bond, or a covalent bond, is going to be single, double, or triple really comes down to factoring in how many additional electrons the atom needs to fill its valence shell. If the atom is going to be making covalent bonds, then overall it wants to make as many covalent bonds as electrons that are needed to fill that valence shell. So for instance, if we look at carbon, which is an atom that we're going to very often see, carbon has 4 valence electrons, right? Since the shell, the second shell, has a capacity of 8, basically carbon needs to have 4 more electrons in order to fill its valence shell. And because of that, carbon is going to typically attempt to make 4 bonds, covalent bonds, with other things. In each one of these pictures, if you add up the number of lines stemming from carbon, it always adds up to 4. It's just doing that in different arrangements. Okay, but what about if we have 2 atoms that are really unevenly matched in their electronegativity? Okay. In those cases where one atom has a really strong pull for the electron, and the other one has a really weak pull, we won't end up with sharing. Instead, what will happen is the electrons will actually be transferred from one atom to the next. Typically, we would say that if you have an electronegativity difference between 2 or above, you're going to see something called an ionic bond, where electrons are actually transferred from one atom to the next. So for instance, an ionic bond forms between sodium and chlorine. If we take the electronegativity difference, so 3.16 minus 0.93, we should get a difference of 2.23, which is greater than 2. So chlorine clearly has the much higher electronegativity, and it's really got a much stronger pull than sodium. So you can kind of see in this picture what's happening is that the electron is being taken from the sodium and is being permanently added to chlorine's valence shell. Now, you might be asking yourself, how does this tether atoms together, right? If I'm simply giving an electron from one entity to the next and they're not being shared, how does that hold them together? Well, remember, whenever electrons get transferred, they end up causing changes in the charge of the atom overall. And actually, what they form is ions, hence the name ionic bond. So let's look at our sodium and our chlorine pre-transfer. Sodium has 11 protons in the nucleus, positive charges, and it has 11 electrons. So we would say that it's a neutral because our positives are equal to our negatives. Similarly, chlorine has 17 protons and 17 electrons, so we are once again neutral. But that's not going to be even once a transfer takes place. Once we've taken an electron from sodium and we've given it to chlorine, now sodium has lost an electron, and as a result, it now has more protons than it does electrons, meaning it's got more positives than negatives, so it's going to have an overall positive charge. Chlorine just gained an electron, so now it has more negatives than it does positives. We would say it's an anion, so it has an overall negative charge as a result. And what do we know? We know that opposite charges attract to one another. So what's going to happen is that all of those positively charged ions, the ones that gave up their electrons, they're going to be attracted to all of the negatively charged ions that just gained electrons, and it's going to hold them together into this matrix, kind of alternating positive, negative, positive, negative, and it's going to create this crystalline structure called a salt. Okay. Before we kind of close out on these bonds here, I just want to talk about one last factor, and that is that they differ in the strength in which they hold together their atoms. So let's go ahead and talk about bond strength quickly. Of all of the bonds that we just talked about, we talked about 3 of them, right? We talked about non-polar covalent bonds. We talked about polar covalent bonds. And we talked about ionic bonds. All of these are going to hold together atoms making molecules. But they're not all equal in strength. And when I say strength, I'm talking about how difficult would it be to break that bond. Kind of what we find is that our non-polar covalent bonds are the strongest, followed by polar covalent, followed by ionic. So they're listed in order of descending strength. It would take the greatest amount of energy to break a non-polar covalent bond. And incidentally, these are also the bonds that store the greatest amount of energy. So we can store more energy here. Those are the strongest. It would take less energy to break a polar covalent bond, and is also a place where less energy can be stored. And then finally, ionic bonds are the weakest and would be the easiest to break, and would be kind of the house the least amount of energy within the bond that's present.